Today, you'll learn to draw Lewis diagrams of covalent molecules, which show all the valence electrons in a molecule, like this water molecule here or this chlorine molecule here. Remember, most atoms form bonds in order to have 8 valence electrons. Now, there are 3 common exceptions to this rule, and we'll get to that in a moment. But first, we need to look at how many valence electrons we expect to find in different atoms on the periodic table. If you don't already know how many valence electrons are associated with each group on the periodic table, please add these blue numbers to your periodic table and work on memorizing them, because you do need to know the number of valence electrons associated with these main group elements. So, which elements do not need to have 8 valence electrons in order to be stable? Hydrogen forms molecules to reach just 2 valence electrons. Beryllium has 2 valence electrons, and it forms molecules to reach 4 valence electrons. Boron has 3 valence electrons, and it forms molecules to reach 6 valence electrons. Here are the steps to draw Lewis diagrams. Step 1. Find the total number of valence electrons in the molecule. Step 2. Arrange the atoms so that the singular atom is in the middle. If carbon is in the molecule, it always goes in the middle. And hydrogen can only form one bond, so it can never be in the middle. Next, form bonds between the atoms. And covalent bonds are made up of 2 electrons. Next, distribute the remaining electrons to give each atom an octet, except for those exceptions: hydrogen, beryllium, and boron. Lastly, if there aren't enough electrons to go around, you may need to form double or triple bonds, and we'll look at those examples later. Let's follow those 5 steps to draw the Lewis diagram for carbon tetrafluoride. Step 1 is to find the total number of valence electrons. Because I have 1 carbon, and carbon has 4 valence electrons, there are 4 electrons associated with carbon, and we have 4 fluorine atoms. Each of those has 7 valence electrons, for a total of 28 valence electrons. Adding 4 plus 28 gives us a grand total for the molecule of 32 valence electrons. Step 2 is to arrange the atoms so that the single atom is in the middle. Carbon is always in the middle. It's also my single atom, so it goes in the middle of this arrangement with 4 fluorine atoms surrounding it. Step 3, form bonds between atoms. We're going to draw 1 bond from carbon to each of the fluorines. So we've drawn 4 bonds, and each bond represents 2 electrons. So we've used up 2, 4, 6, 8 of the 32 electrons we started with. If we subtract those 8 electrons from the 32 electrons, we have 24 electrons left to add to our Lewis diagram. Step 4 is to distribute the remaining electrons to give each atom an octet. Well, carbon already has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. So carbon doesn't need any additional electrons. But right now, each fluorine only has 2 electrons around it. So each fluorine needs 6 more electrons to have an octet. Six electrons plus 6 plus 6 plus 6 makes 24 electrons, and that's how many electrons we had left to add to our diagram. There's no need to move on to step 5 because we do have enough electrons to give all our atoms a full octet. So let's do another example. Beryllium dichloride. Now, even though beryllium is a metal, it is the most electronegative metal, so it can form covalent bonds. Let's follow our 5-step process for this example. Step 1 is to find the total number of valence electrons. Beryllium has just 2 valence electrons. Each chlorine atom has 7 valence electrons. 2 times 7 is 14. And if we add the 14 electrons to the 2 electrons, we have a grand total for our molecule of 16 valence electrons. Step 2 is to arrange the atoms so that our singular atom is in the middle. So we're going to put beryllium in the middle, surrounded by chlorines. And we form bonds between the atoms. Covalent bonds are made up of 2 electrons, so I have drawn 4 electrons so far in my diagram. So subtracting those 4 bonding electrons from my total of 16, I have 12 electrons left to draw. I'm now going to distribute my remaining electrons to give each atom an octet, except for hydrogen, beryllium, and boron. I do have beryllium here, and I need to remember that beryllium only bonds to achieve 4 valence electrons. 1, 2, 3, 4. Beryllium already has the 4 electrons I expect it to have, so my remaining 12 electrons must go around the 2 chlorine atoms. Counting up the electrons that I've drawn, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used up all of the remaining electrons that I need to add to my molecule. And each atom in the molecule now has either a full octet or the full number of valence electrons I expect it to achieve in the case of beryllium. Each chlorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And beryllium has 1, 2, 3, 4 electrons around it. So again, there's no need to go on to form double or triple bonds. You can try for yourself to draw Lewis diagrams for these 3 molecules. Please pause the video for a moment while you work through the problems before I reveal the solutions. And here are the solutions to those 3 problems. So far, all the examples we've looked at have only had single bonds, so let's look at an example that has a double bond. Some elements, especially carbon, nitrogen, and oxygen, can share more than 1 electron pair to form a double bond or a triple bond. A double bond is a covalent bond produced by the sharing of 2 pairs of electrons, so that's 4 electrons total. A triple bond is a covalent bond produced by the sharing of 3 pairs of electrons, that's 6 shared electrons total. So let's follow our 5-step process for drawing a Lewis diagram for a molecule that has a double bond. Step 1 is to find the total number of valence electrons in the molecule. Carbon dioxide has 1 carbon atom, which has 4 valence electrons, and 2 oxygen atoms, which each have 6 valence electrons. So the whole molecule overall has 16 valence electrons. Step 2 is to arrange the atoms so that the singular atom is in the middle, generally speaking, but if carbon is present, it always goes in the middle. So here I've put carbon in the middle. And now step 3 is to form bonds between the atoms. So I draw in a bond between carbon and oxygen, a bond between carbon and oxygen. That's 1, 2, 3, 4 electrons I'm using for bonding. And I subtract that away from 16 to find that I'm going to have 12 non-bonding electrons to add to my diagram. Step 4 is to distribute these remaining electrons to give each atom an octet. Well, to give oxygen an octet, oxygen only has 1, 2 electrons, so it needs 6 more. This oxygen also needs 6 more electrons, and carbon has 1, 2, 3, 4 electrons around it, so it needs 4 more electrons. So if I draw in all those electrons, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. That's more than the 12 electrons I'm allowed to add to my diagram. Step 5 tells me that if there aren't enough electrons to go around, I need to form double or triple bonds. So let's take away a few of these non-bonding electrons and instead replace them with a double bond between this carbon and this oxygen. I now have 1, 2, 3, 4, 5, 6 bonding electrons, leaving me with 10 electrons that I can have as non-bonding electrons. But according to my diagram, I still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 non-bonding electrons. I still have too many non-bonding electrons in my diagram. So I'm going to have to take a few more electrons away and replace them with another double bond. I now have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, which means I can place 8 non-bonding electrons in my molecule. And that is in fact what I have. I have 1, 2, 3, 4, 5, 6, 7, 8 electrons that are not bonding. And so my total electrons in this diagram is 16, which is the number of valence electrons that I'm supposed to have. Each atom does have a full octet. Each oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it, and carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it. So this satisfies all of my rules, and this is the correct Lewis diagram for carbon dioxide. You can try a few more examples with multiple covalent bonds. You can pause the video to work them out yourself. And now I can reveal the answers.